Okay, we are on Unit 2, Notes 2, Section 2 of Unit 2. This is the section on related rates. And related rates are problems that are an application of implicit differentiation that we did in the first section. Often, we are finding the rate of something with respect to time. So when you see rate, think derivative. Because derivative is the instantaneous rate, right, of change. So when you're finding the rate of something with respect to time, most of these you're finding the instantaneous rate, so that would be the derivative. So again, when you see this, think derivative, okay? All right, and in these application problems, a lot of times our independent variable is time, okay? So it's going to be with respect to time. So, all right. Let's go ahead and dive in. So again, we're using implicit differentiation on an application problem, a word problem, okay? Well, this first one is not so much a word problem. It's just, here is an equation, and we're supposed to find dy dt when x is 4, given that dx dt is 2 when x is 4. Okay, so I'm going to take my equation, okay, since we have, by the way, since we have a lot of these longer problems, to save class time, this is one of the few times when I give you a set of notes to fill out, and it's only because I want to save time. I don't want you guys to spend 15 minutes copying down problems. I want to get right to the problem. So, all right. So we're finding dy dt. So focus in on that little variable down there. That's what tells you what to take the derivative of both sides with respect to. So we're taking the derivative of both sides here with respect to t. With respect to t. Okay, last section we always did it with respect to x, now it's with respect to t. And you can tell which one it is right there, okay? So the derivative of y with respect to t would be 1 dy dt, right? So just dy dt. Over here, the derivative of 5x squared with respect to t would be 10x dx dt, right? 10x dx dt. The derivative of negative 6x with respect to t is negative 6 dx dt. And the derivative of 2 is 0. Okay? Now, after we take the derivative, now I'm going to plug in what values I have. So I know that dx dt is 2 when x is 4, and I'm looking for dy dt when x is 4. So I'm going to be plugging in 4 for x and 2 for dx dt. Okay? So I need to communicate what I'm doing. So I'm going to say when x equals 4. When x equals 4, dy dt will equal 10 times 4 times 2 minus 6 times 2. Of course, you could take that dx dt out, right? So it would be 10x minus 6 all times dx dt. That's fine too. Okay, this would be a safe stop spot. Of course, we can simplify that, and if you simplify that, that simplifies to 68. Okay? Now, another way to notate this, instead of writing when x equals 4, I could have said dy dt at x equals 4 is equal to that. Okay? I could have written, instead of writing out when x equals 4, dy dt is equal to that, I could have just written dy dt at, this is the notation for at, it's a long line right there, it's a vertical line. And then down here you put whatever you're putting in for x, y, t, whatever, okay? All right, let's go on. All right, a pebble is dropped into a calm pond, causing ripples in the shape of concentric circles. The radius of the outer ripple is increasing at a constant rate, derivative, of 1 foot per second. So let me read that again. The radius is increasing at a rate of 1 foot per second. Okay? Right there, that told me dr dt, because it's the rate of the radius, and I know that it's with respect to time because look at this unit right here. This foot is the units for the radius. The seconds are the units for time. So dr dt is equal to 1 foot per second. Okay? When the radius is 4 feet, find the rate at which the area of that circle is changing. So we want the rate at which the area is changing. So we're looking for dA dt, where A is area, and specifically we're looking for the dA dt when the radius is 4 feet. So I'm going to say when r equals 4. That's what we're looking for. I like to, over here, sometimes I like to write what I'm given and what I'm trying to find. It helps me keep everything in order. It's like number 1, they kind of really just said what you're trying to find. Here, they write what you're trying to find in meaning. This is the meaning of these things, okay? All right. So we want to begin with an equation. We want to find an equation that relates our two things we're trying to find. So, or not two things we're trying to find. The thing we're trying to find, area, with the thing we're giving, the radius. So that relates A and R. So what equation do we know of that relates the area of a circle with its radius? Well, area of a circle is pi r squared. That is a formula that you are expected to know. So if you don't know it, learn it. Got to know that. Okay? It will not be given to you. Area of a circle, circumference of a circle, some basic areas of rectangles and stuff, triangles, those are never given to you. Some equations are given to you, but those basic ones are not going to be given to you. So you need to know those. Okay? So there's our equation that relates A and R. Now we want to get the derivative involved. So let's take the derivative of both sides. I didn't really leave myself much space here, but I'm going to take the derivative of both sides with respect to t, right? With respect to t, like that, okay? So over here I will have dA dt, and then here the derivative with respect to t of pi r squared. Pi is just a constant, you guys, so don't treat pi like a variable. It's not. It's just a constant. It's like a 5. What would you do if this was 5r squared? You wouldn't treat the 5 like it was a variable and use the product rule, right? Pi is just a constant. All right, so 2 pi r to the first dr dt, right? So take the derivative, and now after you take the derivative, never before you take the derivative, always after you take the derivative, now plug in the numbers that you know. Okay, I know that dr dt is 1, and I want, and that's a constant, right? So it's always 1, so I can put 1 in place of dr dt. And then I want dA dt when the radius is 4. So I'm going to say at r equals 4, or you could say when r equals 4, dA dt is equal to 2 pi times 4 times 1. Say stop. So I found the rate of change of the area with respect to time when the radius is 4 feet. Of course, if this was a multiple choice answer, it would be in 8 pi. All right, now a word about units. Notice that I did not put units in my answer, and the reason I didn't put units on my answer is because they didn't tell me that I had to. Okay, if they want you to put units, they will definitely tell you to put units. Okay, now it's not wrong to put units when they're not asked for, as long as they're correct. If you write units and they're not correct, then you may not get the answer point. Okay, so be careful. If you go ahead and write units, make sure they're correct. Okay, now if they tell you to write units, then you have to write the units, and of course you want them to be correct. All right, now if they had asked for units here, here's how you tell units. I want units of A, I want units of area divided by units of time. If the radius is in feet, then what would the area's units be? Well, the area's units would be in feet squared, because area is, it adds that second dimension. Okay? Time is in seconds. So remember, units for the top over units for the bottom. Okay? And that's how you always get your units. Sometimes I have kids that are just not real familiar with that stuff. So it's an easy thing to get right. And so make sure you get that right. Okay. Example 3. Water runs out of a conical tank. We have a conical tank at a constant rate of 2 cubic feet per minute. 2 cubic feet per minute. We have a conical tank. This is a common thing for them they like these conical tanks. And I'm going to draw this conical tank kind of like this. Okay, and water's in there and it's flowing out. Maybe there's a little hole at the bottom. Okay, it's running out at a constant rate of 2 cubic feet per minute. Well, it's a rate, so I know it's a derivative. It's the derivative of what with respect to time? I know it's with respect to time because of the minutes. What aspect of this cone would have the units of cubic feet? Well, cubic indicates volume. Okay, so they're telling me that dV dt is this constant rate. So I'm going to write down what I know. So I'm given that dV dt is equal to, all right, now I need to be careful here. Water is running out. So is the change in volume going to be positive or negative? Well, it's going to be negative. It's going to be a negative 2 cubic feet per minute. Okay? Be careful with that. If water is running out, then the change in volume will be negative. The change in height will be negative. The change in radius will be negative. All the units will be negative. Because if water is running out, everything's going to be negative. So what if water was filling up? Then all the rates would be positive. In example 2, the circle's radius was increasing, right? So its area was increasing as well, and we found dA dt to be positive. Does that make sense? Of course, because these concentric circles were getting bigger. Okay. All right, so be careful with that. All right. The radius at the top of the tank is 5 feet. The radius at the top of the tank is 5 feet. And the height of this tank is 10 feet. Well, what does that mean for us? That means that in any, well, let me finish reading the problem, but that's what they gave us there. Okay. How fast is the water level decreasing Well, water level would be the height, right? That would be the height. How fast is the water level decreasing when the water is 4 feet deep? So there's water in here, and it's going down, right? Here's the water. It's going down. We want to know how fast the water level is decreasing. So are we not looking for dH dt? We're looking for dH dt when the water is 4 feet deep. So when h equals 4. That's what we're trying to find, okay? We have dV dt. We're looking for dH dt. And this is one of the, they don't expect you to know the volumes of all the cylinders, and oh, this is written wrong. That should say cone. I need to go correct that. That should say cone. Alright. The volume of a cone is given by this equation. If it was a cylinder, it would not have that 1/3 out in front. Okay. But anyway, they will give you that. Alright. Now, in a cone, the reason they gave us this 5 and this 10, when that really doesn't have, well, it's not obvious what it has to do with the water that's inside here. The reason is because the ratio of R to H will be the same throughout this right circular cone, okay? So, in other words, R is to H as 5 is to 10 all the time in this cone, So this gives us a way to write R in terms of H or H in terms of R. So I'm going to go ahead and just solve this for R. We might end up having to solve it for H, but I'm just going to take H to the other side, and so R is equal to 1/2 H. All right. So let's take our equation, and we have V is equal to 1/3 pi R squared H. We know dV dt. We want dH dt. If we take the derivative right now, we have two variables here. So we're going to need to know dr dt, and we do not. We do not know dr dt. So we want to replace R with H's, if possible. And of course it's possible because look, we have this right here. I can put in place of R, I'm putting 1/2 H. So V is equal to 1/3 pi times 1/2 H squared times H, which I'm going to simplify. This is 1/3 pi times 1/4 H squared times H, which is pi over 12 H cubed. Okay? You guys simplify this and then take the derivative. Okay? Do not try to take the derivative of this. I've seen kids do that, where they'll use like a chain rule, they'll use product rule. Oh my goodness. I'm like, they're all H's. Why would you do that to yourself? Make it an H cubed. Okay? Alright. Now that you've simplified it, now take the derivative of both sides. So derivative of both sides here with respect to t. So dV dt is equal to 3 times pi over 12 is pi over 4. Decrease your power by 1. dH dt. Okay? Now plug in your numbers. So when H equals 4, dV dt is -2, H is 4, and we just solved that for dH dt. So we have -2 is equal to 4 pi dH dt. So dH dt is negative 2 over 4 pi would be a safe stop. Negative 1 over 2 pi would be our multiple choice answer. Okay. Okay. I'm looking. I like to look back at the problem to see did they want me to give them units, and they didn't. They did not specifically ask for units, so I'm not going to give it to them. If they had, units for h is in feet, units for time is in minutes. So if they had asked for units, it would have been foot per minute. Okay? Does it make sense that dH dt is negative? Yes, because water is running out. Okay, next steps. Example 4. We've got a ladder leaning against a wall. Okay? A 13-foot ladder is leaning against a wall. Suppose that the base of the ladder slides away from the wall at a constant rate of 3 feet per second. Now let's look at what's happening. We have a ladder leaning against, I'm assuming that wall and the floor are vertical and horizontal. In other words, I'm assuming that they meet at a right angle. And we have this ladder leaning against the wall. So I'm going to draw the ladder. Okay? The base of the ladder slides away from the wall. So the base of the ladder is coming out this way at a constant rate of 3 feet per second. That's a derivative. Derivative of what? Well, I'm going to label this x. So they're giving me that dx dt is equal to 3. Should I make the 3 positive or negative? Is x increasing or decreasing? Well, x is increasing, so dx dt is positive. Okay? Continuing with my little drawing, the ladder is always 13 feet. It's not changing. The ladder is not changing its length, so label it 13. This side, however, is changing, so I'm going to label that a variable y. And it's changing because as the base slides away from the wall, that ladder is going to fall down the wall on the height. Okay? I like to label anything vertical y and anything horizontal x, but you can certainly label those anything you want. Okay? How fast is the top of the ladder sliding down the wall when the base of the ladder is 5 feet from the wall? So we're looking for how fast, that's a rate, the top of the ladder slides down, so we're looking for the rate of change of y when the base of the ladder is 5 feet from the wall, so when x equals 5. That's what we're looking for. Okay, we need an equation that relates x and y. And preferably only x and y, but sometimes you have to get other variables involved as well. But preferably only x and y. Okay, well, we have this diagram, and since it's a right triangle, the Pythagorean Theorem holds true, right? So Pythagorean Theorem will work for us here. We know x squared plus y squared is 13 squared. So we're going to take the derivative of both sides with respect to t. And we will get 2x dx dt plus 2y dy dt is equal to the derivative of 169, which is 0. Okay? Once you take the derivative, you can plug in your values. So when x equals 5, we'll have 2 times 5 times dx dt, which is 3, plus 2 times, okay, we need something in for y. So what is y when x is 5? So when x is 5 and y is what? Well, we have a 5, 12, 13 triangle, And that's a Pythagorean triple. If you didn't remember that, then you would come off to the side and say, okay, I have 5 squared plus y squared is equal to 13 squared, and you would just solve that for y. You get y squared is 169 minus 25. That's 144. So y would be 12. So either know that it's a 5, 12, 13 triangle, or go off to the side and find out what y is. So y is 12 when x is 5. So I'm putting 12 in for y. And I'm looking for dy dt. And now I just solved that for dy dt. So dy dt is equal to negative 2 times 5 times 3 divided by 2 times 12. That would be a safe stop. And as a multiple choice answer, it would be negative 5/4, right? And now, they did ask for units of measure here. So what will the units of y and the units of t be? Our units here would be feet per second, okay? Feet per second. So if they ask for units of measure, this is how they will do it. They will use this exact phrase. Indicate units of measure. That's what they say if they want you to give units, okay? All right, example 5. In the above example, that 13-foot ladder leans against a wall, making an angle with the flat ground. The ladder is now falling down the wall at a constant rate of 0.5 feet per second. So let's draw what's going on again. We still have this ladder, still leaning against the wall. The top is falling down at a rate of 0.5 feet per second. So they gave us dy dt is equal to negative 0.5 or 1/2, however you want to say that, feet per second. Okay? I know it's negative because that ladder is falling down, so y is decreasing. X will be increasing. Okay? At what rate is the angle between the ladder and the ground changing? So we want the rate that an angle is changing between the ladder and the ground. So it's down here. I'm going to call that theta. So we're looking for d theta dt when the top of the ladder is 5 feet from the ground. So that's y. So when y equals 5, that's what we're looking for. Okay? And again, we need to indicate units of measure. So let's not forget to do that at the end. Okay? All right. So now I need an equation that relates y and theta, and preferably only y and theta. I would prefer not to have x involved with my equation, if possible. Sometimes it's not possible, but if possible, that's what I want. All right? So what equation do you know of that relates theta and y? We do know that that length is 13. What equation do you know that it relates theta and y? Well, sine does, right? SOHCAHTOA. Sine is opposite over hypotenuse. So sine of theta is y over 13. Opposite over hypotenuse. SOHCAHTOA, right? We could have used tangent, but then we would have had x involved. And then we would have needed dx dt. And we would have had to go off to the side and find dx dt. Is that possible? Yeah, we could do that. Using the Pythagorean theorem, we could do that. But you don't have to here, because you can use sine and then you don't have to have x involved at all. Okay? All right. Take the derivative of both sides with respect to t. The derivative of sine theta with respect to t will be cosine theta d theta dt. And the derivative of y over 13, You guys, y over 13 is equal to 1/13 y. Always think of it, when there's just a number on the bottom, think of that as part of the coefficient, okay? If you think of it as part of the coefficient, it's just easier to take the derivative of it, okay? So the derivative of y over 13 is 1/13 dy dt. And now that we have now that we've taken the derivative, we can go ahead and plug in any values that we have. Okay. So we want to plug in, we are going to be plugging in negative 0.5 for dy dt. But here I need to plug in something for cosine theta. So, and we have this y is equal to 5. So let me redraw this triangle. Oops. Let me redraw this triangle. Now we're plugging in y equals 5. So I'm going to say when y equals 5. Okay, so when y equals 5, that is 5. This is 13. So this side must be 12 because it's a 5, 12, 13 triangle. You guys, what is cosine theta? What is cosine theta when y is 5? Well, cosine theta is adjacent over hypotenuse, right? So 12 over 13, right? So cosine theta, in place of cosine theta, I'm putting 12 over 13 because that's what cosine theta is. D theta dt is equal to 1/13 times negative 0.5, which is, I like fractions, I'm going to put negative 1/2 in there for that. Okay? And now we just solve it for d theta dt. So d theta dt, if I multiply both sides by 13, they're gone, right? And then I'm just going to divide both sides by that 12. So it'll be negative 1 over 2 times 12. Okay? That's d theta dt. We need units of measure. So I need units of theta divided by units for time. I know it's going to be per second, but what are units of theta? In calculus, units for theta are always radians, you guys, always. So this would be in radians per second. In calculus, always radians, okay? All right. One more example. We've got, let's see what it says. A 6-foot tall man walks at a rate of 5 feet per second toward a 16-foot tall light pole. When the man is 10 feet from the base of the light pole, at what rate is the length of his shadow changing? Gosh, I love these problems. I really do. Related rates problems to me are so much fun. Anyway, I hope you think they're a little bit enjoyable. I do. Most of my calculus students are not crazy about related rates problems, but they are very, the process for evaluating them are it's all very much the same. Write an equation that relates your variables. That's why they call it related. Okay. Find the derivative of both sides. That's why they call it related rates, because you're relating the rates. Okay. And then plug in your numbers. It's not that bad. Equation, derivative, plug in your values. So anyway, this is a fun one though. All right, so we have a man walking toward a 16-foot tall light pole. So I'm going to draw my little light pole here. Here's my light pole. It is, I'm going to assume that it's vertical, not leaning. Didn't get hit by a truck. 16-foot light pole. And this man over here is walking. I'm assuming he's walking on level ground. Okay. And he's walking toward a light pole. He is 6 feet tall. Okay. So he's walking this way. When the man is 10 feet from the base of the light pole, now I don't want to put 10 down here, because is this distance changing? If something is changing, do not label it a number. Label it a variable, okay? Anything that's changing, you make it a variable. And this is definitely changing. It's horizontal, so I'm going to label it X. So he's walking at a rate of 5 feet per second, right? So what is that? That's our dx dt. So dx dt will be, all right, is x increasing or decreasing? Well, x is decreasing, so dx dt will be negative. If x is decreasing, dx dt is negative. So negative 5 feet per second. Okay, when the man is 10 feet from the base of the light pole, at what rate is the length of his shadow changing? So do you agree that he is going to have a shadow, and the shadow is going to be falling behind him because the light from the light is coming like here. So his shadow, I'm going to write a little cursive S, otherwise my S's tend to look like 5s. So that's a little cursive S for shadow. You can call it another variable if you want to. You can call it whatever, M, N, whatever. I'm going to call it S for shadow. So we're looking for ds dt when the man is 10 feet from the base of the light pole, so when x equals 10. That's what we're looking for. So we need an equation that relates x and s. Do you know of any equation that relates x and s? And if we were in class, I'd sit here and I'd, let you guys think on that. There's usually, 1 or 2 people in class who would come up with this. I'm asking you to think back to geometry, and it's been a little while since you had geometry. But this big triangle is proportional to this little triangle. Okay, they're proportionate, which their ratios are the same. So 16, the big triangle height is proportional to the big triangle leg, this leg. The ratio of the height to the leg is the same as the ratio of the man's height to that triangle's leg. So 16 is to x plus s as 6 is to s. So you set up a little proportion that gives you your equation that relates x and s. Now before I could go ahead right now and take the derivative, but I choose to simplify this and then take the derivative. But I could come in and take the derivative of both sides right now. It just would be just a little bit more complicated. But I'm going to cross multiply here. And then combine my like terms, and I'll have 10s is equal to 6x. And I could divide both sides by 2 if I wanted to, but I think I'm just going to go ahead and take the derivative of both sides with respect to t. Okay? So this will be 10 ds dt is equal to 6 dx dt. And now plug in your numbers. Equation, derivative, plug in your numbers. So let's see, ds dt, and I'm solving for ds dt. I want ds dt when x is 10, but if you look, there's no place to plug in x. So I don't have to say when x is 10, because this is going to be true all the time. And if it's true all the time, I don't have to say that it's true only when x is 10. So ds dt will be 6 divided by 10 times dx dt, which is negative 5. Okay? I just look. I always do this. I wait till the end to see if I have to write units or not. So they did not ask me for units, so I'm just going to stop there, save style. Of course, if you have this as a multiple choice question, this is negative 30 over 10, so that's negative 3. Okay? Alright, a little FYI here. What if they had asked for the, what if they said at what rate is x plus s changing? What if they had asked that? So they would be asking, what is the derivative with respect to t of x plus s? Well, that derivative is 1 dx dt plus 1 ds dt. And now we know that dx dt was negative 5, ds dt is negative 3. So this entire length is changing at negative 8 feet per second. Okay? Alright. Fun stuff. I really do love related rates. They can get pretty complicated, but the process is always the same. Get your equation. Try to get your equation with only the variables that you know or are trying to find. But get your equation, take the derivative, plug in your numbers. Not bad.